Many thanks for all of you turning up on a day when the rest of campus is empty. Back in 2013, I was asked to explain what on earth I thought I was doing up here. So I witted a bit about old walls and breakwaters. But at the end of it, I included a few slides on tsunamis because it seemed fairly appropriate, and a number of people found that quite stimulating. So I'm picking up on where we went in 2013. A little bit of background to the various things we've done. The device is called a tsunami simulator. It used to be called a tsunami generator, but somebody decided that wasn't appropriate and would frighten the residents of Oxfordshire if they thought we were actually making real tsunamis. In the preparatory bit, I will talk a little bit about our colleagues at University College London, who've won a number of big projects, and we've joined in with them. The main part of this presentation is the work of a visiting researcher called Roberta Riva, and she picked up something where I said, well, when UCL have finished with the flume, can we have a play? Because it was very frustrating the first time they went in. There was a lot of concentration on detailed, complicated measurements, and they went tits up. The load measuring device was over-specified, and they didn't get anything useful out of it. And that was deeply frustrating because I felt that if we'd done some playing, and anyone who works with big bits of kit know that when you first start out, you want to go and play with it and test its limitations. Preferably don't try and break it immediately. So the sliding building experiments are the main guts of today. I'm mostly thinking of subduction zone tsunamis in here, and the fact that if you're on one side of a subduction zone, you will almost always get a trough-led tsunami. So the 2011 Tohoku tsunami should have been trough-led. The one that hit the Thailand coast in 2004 was trough-led. And in general, the crest-led tsunami disappears out into the open ocean. 2004 was a bit different, but in the main, they radiate out and do less harm. What we're doing in these studies may be appropriate for these, but I paid less attention to those in the generation of. Now, there are various attempts to build tsunami test facilities around the world. In general, they consist of two types. One, you take a big piston and shove it forward in the water, or you drop a weight into the water. So these are sort of the landslide ones, and these, in theory, are the tsunami-genic ones. It's a pity because they've lost track of some work by a guy called Hammermack, who did actually move the floor of his tank to make the tsunami. And that possibly was a better way of doing it. But the key thing is, look at the period. This is 2004, and this was a Belgian yacht, and he had his echo sounder running, and he heaved up on the wave, etc. And if you invert his record, you get this record of the wave. So down to about -3, up to +3.5, so about a 6 metre high wave, trough-led, and lasting for about 120 seconds, so about 20 minutes. That's the crunch. Almost everybody else's attempts to make tsunamis don't get anywhere near there. So this was the concept, which was I worked out that if I was going to generate that tsunami with a piston paddle, I would need one about 15 meters long to be able to reproduce a tsunami at a sensible scale. By that I was imagining 1 to 50 to 1 to 100. So 15 meters stroke. At the time, I couldn't work out how you do that. I had a bit of a problem. Plan C was dump a concrete block into the water, which is what the Cambridge academics had done. And that struck me as almost completely useless, even if it got lots of publicity. So plan A was to suck the water out of the flume up into a tank here using an air pump, and then control the air going back into the tank to allow the water to move up or down as you're trying to generate the wave. And this was the first generation, and a sneaky tip is, if you want to make your facility look bigger, choose a very small research assistant. A warning, however, Ingrid is a competition weightlifter, so you didn't give her any cheek, even if she was only little. So this was the tsunami generator missing its front face. These are the baffles inside to stop it sloshing around. Here it is in the flume and here, and there's a small opening down at the bottom. Now that opening produced lots of eddies and lots of energy loss, so we changed it. But this was the attempt in that early era, so this is about 2008, a model building on a force transducer mounted into the bed, and a rather sparse array of pressure transducers. Now this is, I think, where I finished in 2013. The tsunami is coming from behind you. It's done its trough. It's building up. We serendipitously discovered that these concrete walls that we had lying around the lab slid just about at an inundation. They were just about to be overtopped. And we had those buildings got made within days of one of the tsunamis in the lab. The really important thing is the sheer time over which this is still flowing in. And we've now hit the cliff line at the back of the flume, and now we're retreating. And if you had repeated waves, then with the same periodicity, then you'd be caught. This would end about halfway along the scale, and that does indeed sail out to sea. Now those were entirely for demonstration. There wasn't any science behind this little demo. So the important thing, and off to go and join that great big gyre in the middle of the Pacific. So the classic way of generating, trying to generate tsunamis, is to generate the solitary wave as discovered by Scott Russell up on the Union Canal. And this is a translatory wave, and if everything remains perfect, it will maintain its form, so it's stable. Real tsunamis consist of both troughs and crests, and maybe multiple, although that actually might have just been reflections from the Thailand coast. So an adaptation of the solitary wave, but still having some of its limitations, is to make what are known as N waves, either leading depression or leading elevation. And a lot of the classic work is done with those and large amounts of numerical modelling and so on. uses solitary waves. But this shows just how wrong that will be. That's the solitary wave of that wave height, and you can see there is an enormous amount of water and discharge that is left out. This is even, that's 2000, no, this is 2004, that's 2011, Tohoku. And you can see all of this flow that's left out by generating a solitary wave. So a classic paper by Madsen essentially says solitary waves, nothing to do with tsunamis at all. So we've improved the original device with a shaper to help flare the flow out and reduce the back eddies. We're trying to remove the safety valve and just control the control valve with emergency stop switches inside. Suck the water up to make the trough, let it drop under control, make the crest, wave propagation out down the flume. Of course, there's a bit of madness in this, in that our flume is not a kilometre long, and to make these sorts of tsunami waves at true scale, we would need a kilometre long flume. But we thought we would have a go in any case, and it's been mostly successful, and my clever colleague Dr. Ian Chandler has some ideas for making it even more so. So here we have the flow shaper. You can see the velocities here, but the good thing is we've eliminated the back eddy, and we had success with generating the Mercator wave at 1 to 50, all the way out to the end of the first, the trough and the elevation wave. In the recent tests, we've mostly used elevated waves because, of course, on land, the trough doesn't do a lot. The trough is important for the stability of the seabed, for the coast defences, etc. It's deeply important if you think about the geotechnics of perch water table in coastal embankments and in beaches. But for the buildings that we were looking at, not important. So we've just done the elevated waves, and we have some secret codes which are, I'm afraid this is bad practice, but I'm now going to move entirely into model terms, so I'm not translating into prototype. So 20 seconds, 45, 80, we did try at 160, but we never got it to do anything interesting. So it's these three waves that we're running in the tests. And this is us calibrating. That was the elevated waves. These we're calibrating N waves as well. So we know we can generate them. There we go. And that's an illustration. It's gone a bit wobbly. We're having to auto-correct the signal to try and keep it in the flume, but we've got a wavelength of 752 metres and we're generating it in a flume of 100 metres long, which is insane. I mean, it's just a mad idea to even try and do it. And in pure science, I'm sure that there are lots of flaky bits, but in engineering space, it works, and it seems to work quite good. And Dr. Chandler and Dr. McGovern from UCL are busy drafting our journal papers. They've just been to a conference in Canada talking about it. So what was our motivation? Well, the bit that scared the hell out of a lot in the tsunami community was we're expecting buildings, small buildings, vernacular buildings to be swept away. We're expecting cladding to be washed off the face of buildings like that. That's all anticipated. The bit that really scared people is reinforced concrete buildings being picked up and dumped on their side or whatever. Now, generally, you'd have thought in an earthquake zone there would have been tensile reinforcement down into the ground, into the piles. But rather peculiarly, this appears to have either just ripped straight out or perhaps even been missing. And so it's clearly important that we have much better information on tsunami forces on buildings. Whoop, sorry. Now, the science bit, this is the bit that UCL researchers have been doing. And there are two researchers, David McGovern and Andrew Foster. And David has been looking at sea defences. So this is a large tsunami defence wall. That's one of these clever sheets of pressure film. So in theory, that would give us pressure distributions. In truth, a bit of a nightmare in a wet environment, and requires 25,000 quid's worth of interfaces and software to run. The sheets are actually much cheaper than they used to be, but you can't get them wet. So that's a bit of a pain. And here there are other load transducers in this section of wall. These are buildings. This is a very big building, but the same frame has been used to suspend quite small buildings. So when I show one building in Roberta's tests, that's trying to emulate exactly the same as the one building in here. But imagine that I was going out to Joe Public and I was trying to explain what we're doing. Is the average person on the street going to understand what on earth we're about when there's all this stuff in the way? So what I thought is, let's try and have the very, very simplest, grubby experiments, and let's see if we can make them work, however simple they are. So what we built was we built little, if I can use old units, 6-inch cubes, 150 by 150 by 150 millimeters, hollow plywood boxes. Now, they're going to slide on a concrete floor in the flume, like this. So what we did is we gave them a concrete base. We were a bit too pessimistic. I mean, this was our first attempt, and it worked quite well. But if I do this again, I will make this layer about 1/3 as thick, because these were, when they're empty, they were still a bit heavy. They're about 100 tons, equivalent of 100 tons each, which if you start looking at a concrete building with a foundation mat slab, an intermediate floor slab, and a roof slab, actually you don't get, you get a bit more than 100 tons. So we got it reasonably right, but it didn't go quite light enough. And what we did was we had a supply of concrete armour units, little cubes, all made very carefully, all very narrow range of weights, so we could fill up this space with little concrete cubes. So the modus operandi was simply put the building in the flume, run the wave, if it slides, take it out, put some weights in it, and run it again. And that's what Roberta did all the way through the day. Now, she needed about 20 minutes to record all the information, transfer it out, and let the sloshing die down, because a 2 or 3 minute wave just carries on sloshing around in our 100-metre long flume forever, and well, certainly for 20 minutes. So that's something that Dr. Chandler wants to try and eliminate. The tests got so exciting, yeah, exactly, and even a 1 on 20 beach slope acts as a perfect reflector, so it's a pain. But what they're going to do is they're going to detect the returning wave and then auto-correct the signal to dissipated out. The experiments were so much fun that we needed more buildings. Now, I'm doing this on a complete shoestring. Roberta's a visiting researcher from Italy. I'm not paying her very much. I'm going over there as infrequently as I can, because every hour of my time costs when I'm down in Wallingford, and a lot, and so on. So we went raiding, and the really, really useful thing is, what do civil engineers do in their first 2 or 3 weeks in the concrete lab? But they make concrete cubes, and they make 6-inch concrete cubes. So purely by chance, we had a whole load of pretty much 6-inch, they're actually slightly small, 6-inch concrete cubes. So we used those as dummy buildings. And off we went. And we did do the friction tests, and we got a lovely, a blissfully good friction coefficient of 0.73. And so everyone was happy, and off we went. We made E20, E45 and E80 waves, and the miracles of, if I've learnt Joe's training, and lots of time when it doesn't appear to be happening. And why didn't the middle one slide? Because after a few tests, Roberta worked out that it didn't matter which of those buildings she got the heaviest weights in. You know, she could put the heaviest weights here and it wouldn't slide, and the lighter ones there and it would slide. So what she did then was that she had heaviest, lightest and nearly lightest. So she got 3 tests worth of information out in one. Well, not quite 3 tests, because what we're then doing is saying, okay, the answer is somewhere between this one and this one. That's not quite heavy enough. That is a bit too heavy. And my interest stops. Now, I don't care what happens in the processes afterwards. I'm just looking at the onset of sliding. So, to analyse it, we had to try and calculate a buoyancy force. And if we go back, no, yeah, you saw the wave heaping up on the front face, the stagnation pressure, and low down here. So we constructed a simple empirical model of the buoyancy force, and now we know the weight, we've estimated the buoyancy force, and we know the friction. So therefore we can back calculate the horizontal force. Engineering space, but is it good enough? Well, it looks like it. I'm going to jump. We actually didn't call this the base case originally, but now we are. Here, it's a complete wall across our flume. So we've fully done it, and these are the measurement ones, and here we get, and these units have almost no meaning at the moment, but 90 newtons for the horizontal force, E20 and E45. E80, it was still stable. We couldn't get it to slide because these buildings weren't quite light enough. And that's why if we get to revisit this, we will make some lighter buildings to try and get the light blue one here. There is an uncertainty in skipping between the tests. So sometimes the slid may appear to be slightly heavier than the didn't slide. But the margins are very small. So that's simply an indicator of the level of inaccuracy or randomness in the process. So one building on its own. So we're up about 90 for E20, and it drops to about 45, so 50%, which is interesting. So if you had a complete wall across here, the force on each building would only be about twice what it is on a little building all on its own. We started with this as the base case, but as I say, we used the full wall later. So 3 buildings, and actually no real effect. So blockage ratio of 25% hasn't made much difference. It's still as there would be for the single buildings. And that's really encouraging for the UCL brigade, because they now know that their very complicated tests with single buildings are now valid for quite a lot of cases. Actually, it gets even better. And now we're up to 33%, and still we're pretty much the same place. And this is where we put same blockage, but we put 2 buildings together, and pretty much the same. That is the force on 1/2 of that double building. This was interesting. We all thought that if you turned the building through 90 degrees, it would be more streamlined. And therefore, the stagnation pressure on the front would be less, and so on. But the projected area is bigger. The 2 cancel out. That did surprise both the UCL and ourselves. So those hotels that build their bungalows obliquely, they haven't actually, saved any force on the building. Then we carry on with making it more and more dense, and we're still getting about the same force per building. And we turn it obliquely, and has that crept up a bit? Not really sure, because we haven't got a stable one there, but it's probably only just... We've put data in here where Roberta's engineering judgment was it would only take a very small increment to make it stable. And now the blockage is starting to move the force up. Okay, now not many conurbations just involve 1 row of buildings. So most places have multiple rows of buildings. So what happens? And the interesting thing is that the second row is nicely sheltered by the first row. Okay, we'd sort of expect that, and especially if they're in line. As, however, you move them further back, so that's the space between the buildings gets one, then the sheltering effect appears to have died off a bit. But what's going on here? The force on the front row is less. Does that make sense? Set the building further apart and it starts to creep back up again. And these are lower. And what's happening? Well, we'll see it a bit later. Staggered, so these are back where they were previously. These aren't getting much benefit from the front row, so they're being hit. And you'd sort of expect that. You'd expect with this width of spacing, the tsunami wave can come through relatively unaffected, and there'll be a tail of turbulence behind each of these, and a wave going out, but it's not dramatically changing stability there. And more 2 rows staggered, and 3 rows, and now the second row is the worst, and the later ones, and 4 rows staggered, and well, you could go on, but actually now we're straying into the territory that you'd use a numerical model for. So what we're hoping is that by using the UCL detailed measurement, the Wallingford comparative measurements, then we've got a huge raft of calibration work for the numerical modelling that's running both at Wallingford and at UCL. So this is a summary. Obviously this line doesn't go back up and needs a bit of tweaking, but if we call this the origin, the comparative load per building comes down. We haven't got much in this space. That's slightly intentional because there's not likely to be a lot unless you had a huge development or mall and a few little roads between them. So we thought 7 buildings was as dense as we could really do it. So not a lot of information there, but we think that there's an effect in which all of these are pretty much the same sort of load. And that is really good news for the UCL researchers. Roberta hasn't yet teased out what she thinks the lessons are for the multiple rows. One thing that we did find is that there were situations when what would happen is if we have multiple rows, these all hold the tsunami up, but the last row, there's no resistance behind it. And so you get the tsunami peak building up in the conurbation, but then there's a big hydraulic gradient in the last row. So if you had the Sendai plane, it is possible that if all buildings were the same strength, those at greatest danger would be the ones inland and not the ones at the seaside. And that was interesting. I don't think we can make that a universal rule, not with these tests. Okay. And lots of different situations with varying this spacing and blockage ratio. These are just with 3. Yeah, and you can see the various types that she's got. We're some way from being able to explain all of that. Now you've seen that one. That's the longer period wave. So this is the same wave as the one you see with the 3 alone. It will be if it plays. And you can sort of see the point that I was just making there, that the whole of this assembly holds the wave up, and then the hydraulic gradient across the back buildings is the greatest. That's the one that slides. And interestingly, it may be that it was sliding also in the slightly longer period wave. Okay. Right, trying to first sanity check. Let's look at the FEMA, Federal Emergency Management Agency, guidance on tsunami pressures, and it's based on work by a Japanese bunch. Interestingly, Roberta reckons that this is only available in Japanese, so a bit difficult for the rest of us to review. But clearly those who wrote the FEMA guidance could do so. That's the prediction line, and it's clearly safe in relation to our data. And that's good. It means that if people stick to the FEMA guidelines, they're probably going to get a safe answer. And it also means that if our test results can be suitably justified and reviewed, then we can save people work and effort and loads. What she's trying to do is to generate a nominal force from a 2-part term here, but that needs the velocity, and we didn't have velocity measurements in transient dry to wet is a complete bitch. Sontex, etc. drop out the moment you've got air bubbles, and as the interface goes past the head, you usually capture little air bubbles round there. No? Maybe we're a little out of date, but we've... and miniature propeller meters are very, very fussy about super clean water. They don't like dust. They don't like woolly jersey fibres, which get round their rotors. And so we've had a lot of difficulty in measuring velocities, where we're managing to get upward-looking ADCPs in the new series of big tests for UCL. But it's what you're looking at is the bore front, and if anyone knows a whizzo way of measuring velocity in bore fronts, then I'm a candidate for learning from you. So what we've done here, which is a bit clunky, is essentially the same as a bunch of Aussies have just been doing independently, and essentially you define a certain level on a wave gauge and you time how long it takes to get from this wave gauge to that wave gauge and calculate the velocity from that. And it sort of works. Next 3 slides are 3 different attempts to try and harmonise the data, in which she calculates the nominal force by an equation like this with different methods of deriving velocity, and see how good it is. And that one isn't bad. This stays the same because this is just the blockage ratio and the actual measured horizontal force. This is the measured horizontal force too. A different method of determining the velocity, still leaving out these E20 results. Maranpour is a UCL researcher, and this harmonises it a bit, but that point is unsafe. So that's sort of you can have safe, but not fitting the data awfully well, or this fits pretty well, but is that a real point, in which case this isn't a safe prediction. So we've looked at blocking ratio, we've looked at building orientation, we've looked at the effect of the row and rows behind. We're some way down trying to account for different tsunami amplitudes in terms of being able to predict the velocity using numerical models and then apply that in the forces. And our results look as if they are going to be really usefully complementary for the UCL measurements. So definitely one of the parts of a team. Teams tend to have a lot of difficulty and people get very scratchy when different components of the team try to do the same thing. Unless they go into, even if they go into the same facility and all measure it together, they then go off in separate places and write rather different versions of the papers. And that makes a scratchy team. But a team that works nicely is where you've got different parts of the problem being dealt with by the different people. So Professor Tiziana Rossetto is the complete star because she's the one who won, it was she on the headline of the 2 major grants that we won and a subsidiary bit. David McGovern is the prime man working at Wallingford with us and helped occasionally by Andrew Foster. And Roberta is in charge of doing this analysis and running the tests, and Ian is our supervisor. None of this could be done without a whole series of visiting researchers who've done wonderful things and gone out into the world and making their way in industry and in research. So a real team effort. Thank you.
This production is brought to you by the University of Edinburgh.